Louvain-la-Neuve. I was corrected this morning, and he's going to talk to us. And it looks like he's got some very nice pictures, although maybe the colour isn't quite as you would choose.
So thank you for the introduction. Good morning, everyone. So today I'm going to talk to you about a parallel multirate time-stepping strategy that we try to develop for ocean modeling. So this work is done with Jonathan Lambrecht, that is here in the program too, with Thomas Toulor, Vincent Legat, and Jean-François Remac. We are all from the Catholique University of Louvain-la-Neuve in Belgium, in the French-speaking part, because we have two Louvain-la-Neuve, as some of you know. What? I also want to thank the organizers to allow me to present here and to participate in this program. This work is done in the framework of SLIM, that is the model that we developed, the ocean model that we developed in Louvain-la-Neuve, and also with GMesh, that is a mesh generator that is developed by Jean-François Remac, my advisor, and Christophe Gueuzin from the University of Liège. So what we try to do is solve multiscale marine flows, and for these problems we have a large spectrum of spatial and temporal scales. We have here a picture of Vicky that represents the different scales that we can have in ocean modeling, as well time scales as horizontal spatial scales that are related with each other, and so we need to try to solve some of these scales, or as much as we can. So as I said before, we developed, so this is the second generation Louvain-la-Neuve ice ocean model that is called SLIM. We use discontinuous Galerkin finite elements on unstructured meshes that are generated with GMesh. So I gave you here some applications that I will use later in my presentation. Lately we were simulating the Japan tsunami. Here is the initial condition that we used, the world's geometry, the bathymetry, and the mesh. And so the meshes are built to represent accurately the topography, so the coastline essentially. Here we also have mesh sizes that depends on the bathymetry, and we also, in this case, we refine around our interest zone, that is Japan. So another applications that we like to show is the Great Barrier Reef. So in Australia, here you have a zoom on the Whitsunday Islands and the bathymetry again, and the mesh is not very well represented on the screen, but again the mesh is refined with respect to the topography, with respect to the bathymetry, and also to try to accurately represent, solve the scales that are close to the coral reefs. Last application is the Scheldt estuary that is close to Belgium and not so far away from the UK. And here, for example, we also build a mesh, but with a very refined region around the Scheldt estuary that we want to represent. But all these meshes, all these problems, they induce that we have large disparity between time steps, local time steps on elements, due to the unstructured kind of the meshes, but also due to the wave speeds. And as an example here for explicit time stepping, typically between the maximum and the minimum stable time step of the problem, we have a ratio of 721. So this is a big issue for computational efforts, because we want to be as efficient as possible, but we see that it's not efficient to use only the global stable time step of the problem. So just a brief reminder of, I'm going to talk today about explicit Runge-Kutta methods. So you know all this, pros and cons, some of them are listed here under. What is important here is that explicit Runge-Kutta methods are easy to implement and parallelize. So we have very low cost per time step. They are self-starting, flexible, they can go up to very high orders, but you need a large number of stages then. They are easy to manipulate, so we can apply solution limiters and clippers, but the maximum allowable stable time step is limited by this famous CFL condition. And as a consequence, it's extremely inefficient for stationary problems. So it is usual to represent these Runge-Kutta methods with a Butcher tableau. That I gave an example here for a two-stage method, the RK2A method, that I will use later. And so with the colors, you can see, all this. You compute a first current input. After that, you compute the derivatives, time derivatives. You make a first approximation, and after that, you compute from this approximation. You make a second approximation. After that, you sum all this, and you compute the next time step solution UN+1 for a simple ODE. So the time step restrictions, especially for shallow water equations. So the explicit time step is restricted actually by the combination of the finest size of the grid cell and the highest wave advective velocity. So for the shallow water equations, it reads like you have to find on which triangle you will have the maximum ratio between the wave advective speed that is here proportional to the flow speed and the momentum advection and the square root of gravity times the water depth. And this divided by the grid cell size. So in general here we always use the inner radius as measurement for the grid size. As we use essentially triangles, we use the inner radius of this triangle. So here you have all the kind of things that essentially influence this time step, especially since the waves that are ruled by GH are the most important in this computation. So this is very restrictive for highly unstructured meshes and strongly varying wave speeds. And if you want to do long time simulations, this is very inefficient to use explicit Runge-Kutta methods. So what we want to do is try local time stepping. So general idea, here with a very simple example, consider a mesh where you have 3 different time steps, 1/4 delta t, 1/2 delta t, and delta t. So a classical explicit Runge-Kutta time stepping will use the global time step 1/4 delta t, and the number of operations will be 16 elements. We estimate the number of operations as 16 elements times 4, the number of time steps to reach delta t, times the number of stages that you have in your explicit Runge-Kutta method. So we estimate that as 64s. If we would apply a naive explicit Runge-Kutta time stepping method locally, we would use the own time step of each element. So if we have then 3 different time steps, we would reduce the computational cost. It would be 28s, and we would achieve a speed up of roughly 2.3. But how do these groups of elements then communicate? You need to be able to do some kind of interpolation to communicate the information, because they're running at different time steps, so they need to communicate. So what we choose is to explore an alternative that is multi-rate time stepping. They try to preserve the specificities of explicit Runge-Kutta methods and keep convergent conservation, a simple implementation that is very important, flexibility, and high scalability. So we will consider groups of elements. This is the thing about multi-rate time stepping, to use different ratios of time step that are all integer multiples of 2, exponents of 2. So we explored 2 approaches that we found in the literature. One proposed by Constantinescu and Sandu, and one proposed by Schlegel. So the first one, the idea is to introduce buffer groups. We will call them outer buffer groups because they use the time step of the group next to them, the biggest time step between 2 groups of elements that are integrated with their own time step. So the idea is to repeat twice the base method for these elements, to be able to communicate with the small elements that need twice more computations, twice more stages to achieve the same final time step. So they are conservative and preserve the strong stability properties They're generalizable to any explicit Runge-Kutta method, but they are at most second order accurate, whatever you choose as base method, because actually at the interface between the bulk groups and the buffer groups, you lose the convergence up to order 2. So the buffer groups are here always need to be always of the size of the same size as the number of stages that you have in your base method that you use, because actually it's only at an S from S connected elements that another element will not influence the next element. So actually, if you repeat twice the base method, there will be no influence on the next layer of elements. And so there you can use again the same standard explicit Runge-Kutta method. So here, for example, the theoretical speedup will be only 1.6 with for the RK2A method. Schlegel, he proposed a method that borrows some ideas of the IMEX method, and he tried to combine different base methods. Actually, he found for one method, the RK43 method, that you can build a multirate scheme that is third order accurate, but here you will need inner and outer buffer. We will have a lot more stages. It is not really clear if you're going to have conservative or consistency. Actually, if the scheme is not conservative, I will show it after due to the B vectors in the Runge-Kutta method, but you can do a partitioning by fluxes and only take the best flux of one or of the other side, and it is conservative, but then we have really questions about the consistency of the method. So the method is third order accurate for a specific base method. And here we will still have the speedup in depending on the number of right-hand sides that we have to compute.
What's the theoretical speedup? What does that number mean?
It's compared to the single rate method when you use the smallest time step. We compare the number of substantial operations that you will have to perform.
For this setup? For that diagram? Or
yeah.
just for any setup?
No, for any setup. When we use the explicit Runge-Kutta methods, we just evaluate the number of stages that we have to perform, the number of steady state residuals that we have to compute, that are the substantial operations that we have to perform, and we compare how much we will have to make with multirate and how much we will have to
Yeah, but the 2.3 is for this.
It is
what?
The 2.3.
for that arrangement.
Yeah.
I mean, it's, yeah.
This is compared to 2.3 and the 1.6 is compared to if we used the same base method for the same setup but with single rate.
On that grid there.
Yeah.
Not on any grid. I mean, I'm imagining a grid where you have a huge high resolution region and a very few low resolution points, and you're not going to get a speed up of 2.3.
No, but I will show all other results on big grids after. I will show the comparison method. So here's a bit more in detail. So we have in general, we have two bulk groups that are separated by a buffer group. In this case, for the RK2A examples, we have two connected elements. This is especially interesting for discontinuous Galerkin discretizations because the elements are connected by the faces and not by the nodes, so the buffer regions will be a lot smaller. And so we repeat the base method twice in the buffer regions. So that's what it's looked like. So actually, for the red elements, we will have 4 stages. After that, we repeat twice. Actually, the blue one, the blue budget tableau is twice the green one, repeated. And actually, if you apply this one on the green elements, you would find that two steady state residuals are exactly the same in this method. So it's therefore that you can write here only the budget tableau with 2 stages. So in general, we need S-connected elements, and as I said, we have only second order due to interface treatment. It's actually between the buffer and the smaller group that we lose the convergence. For the method of Schlegel, then we have an inner buffer and an outer buffer, and that are always both of size 1. And we use adapted budget tableaus for the inner and outer buffer. So the base method is the RK43 method. Actually, here I show we have in the buffer groups, we have 10-stage budget tableaus, but the 10 stages are necessary to compute the the interface fluxes, but actually you don't need to compute all the right-hand sides for every line of the budget tableau. I plotted them on red. So for the inner buffer that use the smallest time step, we only need to compute, it's 8 actually, and then 4, sorry, and then 4 for the outer buffer method. So this is how the groups communicate. So next, how do we construct the multirate groups in general for any mesh? So we assume that we have the minimum and the maximum stable time step, and what we gonna try to do is choose a reference time step and try to find the multirate subdivision that we will have. And we compute the maximum multirate exponent z star, and that we compute by taking the log 2 of the ratio of the time step that we want to use divided by the minimum time step. Z plus is what I will call the maximum multirate exponent that we can have, so that we have the maximum number of temporal refinements. So after that, we use notations to characterize the elements in the different groups. Theta, that will be modulo 3, 0, then you have a bulk group. Modulo 3 gives 1, then you have an inner buffer group. And modulo 3 gives you 2, then you have an outer buffer group. So for Constantine and Sandu, the first step, we just assign the bulk tags that correspond to the range of time step to which the elements belong. After that, we introduce the buffer groups and we smooth the multirate tags to have a smooth transition between all the elements. In the case of continuous elements, as you can see, the buffer regions would be a lot larger, and we will have a multirate method that is a lot less efficient. But also, it's not clear how you're going to handle the global mass matrix with this. Actually, we didn't really explore that. Next, for Schlegel, first step is exactly the same. After that, we introduce the outer buffer groups, and after that, we introduce the inner buffer groups by taking the smaller elements, and we smooth the multirate tags. In the case of continuous elements here, we would have only buffer elements for this example. Here, I'm not going to spend a long time about this, but you need to know that it's not especially by taking an integer multiple of the smallest time step that you will achieve the best speedup. You could take a smaller time step up to 0.5 times the smallest time step, and you will have other multirate groups than in other cases, because the elements will arrange themselves in another way, and so the speedup can be different. So it's not especially for by taking the smallest time step as smallest time step for the smallest multirate group that you will achieve the best speedup. Just keep that in mind. So here, I'm sorry for the colors. Here are some multirate groups for a two-stage method in the Great Barrier Reef around the Holbourne Islands. Here you have buffer layers of 3, 4. This is for Schlegel with inner and outer buffer groups. This is in the Scale estuary. Actually, what we did here after, because it's not, there are elements, buffer elements that appear that are actually not necessary. I don't know if you can see them, but they are not necessary, and we can just give them the same method as the bulk group that is under, because they are all surrounded by they don't separate two successive bulk groups, but only one. So here, for example, then we remove all the superfluous elements. So they have a small time step, but in practice, they use the same amount of stages as the other methods. So it's better to use a smaller time step, actually, and you will have less groups or disconnected elements. So this is again for 3-stage, 4-stage, and Schlegel with inner and outer buffer groups. So here we will compare about convergence, the multi-rate schemes with the single-rate schemes. So here we just choose a small example with an island in a rectangular basin with bathymetry on the top, and then an initial condition that is an expansional on an instructed mesh here. We can see here for different age, so we divided we refined uniformly the mesh size, and we obtain different speedups and different number of elements, and the time steps are different, decreases, and we have always the speedup that varies, because it's never the same. If you want to do spatial refinement, you won't have the same multirate setup after. So this is purely temporal convergence. This is in function of the CPU time. So here we have the L2 error for the elevation, L2 error for the velocities. Was computed after 0.5 seconds. And we see clearly that for the CPU time, the single rate methods are always more performant, because the global temporal error of the multi-rate schemes will be influenced by the biggest groups. So it's that time step that will influence, after a certain amount of iterations, the global error, but pure temporal error. So you see that all the methods of Constantinescu with the C, they achieve only second order accuracy, even if you get a little better accuracy for the RK44 method, you still have only second order accuracy. But if you look at the space-time, at the space-time refinement, actually only space, but the time step will decrease also, you will see that the RK2AC, the multi-rate method, is the most efficient in terms of CPU time, because the spatial error is completely dominant in general when you use this CFL condition with with low order DG discretization. You will have the spatial error that is completely dominant, and then here you will be really efficient and have the best global accuracy compared to the CPU time. About conservation, the three methods of Constantinescu are perfect conservative. Why? Because when you see the two watershed tableaus between a buffer and a bulk group, the B vectors are always the same. This means that the fluxes are exactly the same at the interface between the groups. It was not the case for the one of Schlegel, but as I said before, if you choose a partitioning by fluxes and you only take the most accurate flux and not compute twice the fluxes, you will have conservative method. But then it's not clear at all if the method is consistent and has important properties. Here are some results for the Great Barrier Reef for a mesh, for the mesh I showed before. So you have actually the alpha star is the factor that you apply to delta t star to have the best speedup. As you can see here, alpha, when you vary alpha, you will have different theoretical speedups that you can compute for the different methods. But it's clear that if you use alpha, that is the factor 0.5, it's exactly, you will obtain exactly the same as for alpha equals 1, because then you will just have an empty group between delta t min divided by 2 and delta t min. This group will be empty. So it's exactly the same, but between them, the elements organize in a different way, and you can have different speedups. So here's an illustration of the time step that are used in the Great Barrier Reef. Here you have 6 levels of refinements, the buffer groups of size 2 at each time, and the two bulk groups are always separated by buffer groups of size 2. And here the smallest time step, the reference time step that is taken is 7.38 seconds. Here are some results for the scale theory. So here you can see for the number of elements I presented before, how the elements are distributed among all the different multi-rate groups. You can see that the outer buffer represents in general something that is around 20% of the number of elements. So there you lose efficiency because you use more stages than you should use by the original time step. But here we have nice speedups from 7 to 9 for Schlegel, and we can see that in practice we achieve speedups that are even a bit better. For the RK, for the method of Schlegel, the last one, RK43S, the effective speedup is lower. This is actually because we use the conservative form, and so between two buffer groups, since the B vectors are different, we compute the interface times twice to ensure consistency. So this is why we have more residuals. So we didn't take that into account for the theoretical speedup, that we will have to compute twice more interface residuals at these interfaces. Here we have just the comparison for the scale array when we launched the simulation for 24 hours of the max elevation, the max velocity, the orthonorm of the elevation and the orthonorm of the velocity, and we compare with the single rate method, and we see that globally we have almost no differences. Actually, the spatial error is dominant, and you see very little variations in the different norms. Now, the last part of my talk is what about the parallel implementation of these multirate methods? There are several issues because you won't be able to apply classical partitioning, mesh partitioning for this kind of problems because the elements have all different costs depending on the group to which they belong, because they will achieve different number of computations. So here I take the example from before again. There you have the multirate tax. Now I show the loads, the multirate loads that are associated with each element, each group. So the smallest elements will have to achieve 8 stages in total, but the buffer elements that are close to them have also to achieve 8 stages. So here we have loads, multirate loads of 8, 4, and 2. So in total, if you take the total amount of elements, you have total workload of 80 for the 2 partitions, and ideally you would like to have 40 work units per partition for 2 partitions. But the mesh partition should be well balanced in terms of computational loads, but you have also to ensure the synchronizations because in total you have different stages. All the cells are not active at the same moment. It will not be sufficient to only say we have the same workload on every processor. The workload should be the same on every processor, spatially and temporally. So at every stage of the multirate algorithm, you should have the same amount of active cells. And what we try, this is a constraint. After that, what we try to minimize is the interprocessor boundaries that represent the number of communications that you will have to perform. And so we try to minimize, because the communications will also be different in the multi-rate case than in the single rate case, because small, very small elements will have to communicate more than large elements. And also we would like to do this communication and perform all the computation that we can do during the scattering process. So here I'll talk a little bit about the partitioning strategy. So just to show you that, to illustrate what I just said, classical partitioning is not working here for small problems. So we have in total 8 stages. We use a 2-stage based method. We have 1/4 delta t, that is smallest time steps. So in total we have 8 stages. If you partition, if you use the classical partitioning strategy, minimum edge cuts, equal number of elements on each partition, you will see that typically you will have this solution to have the minimum interprocessor boundaries, but the workload is not at all well balanced between the 2 processors. And if you count on every stage what you will work and what the other processor will have to wait for synchronization, you see that you are a lot higher, here 56, than the 40 work units without waiting that you should achieve. But you have only 2 interprocessor phases. After that, you could just say, we use single constraint partitioning. You can do that with METIS and assign one unique load that represents the multi-rate load on each element and say, okay, we try to have the same workload on each partition and try to minimize the weighted edge cut that represents the amount of communications. So that would be the solution that you would get for the 2 partitions. But after that, partition 1 will have to work all the time. Partition 2 won't have, he will have only one element that will have to work, that will be active on each stage of the global algorithm. So you will have to wait several times on both partitions because you have to wait the other elements. And so in total, you will also have 56 work times. And here the total communications, the total amount of communications that you will have to perform is 28. So we see that the communications increase, but what we then can do is say, we try to have, we use a multi-constraint partitioning where we ask to have the equal workload, but also to minimize the waiting time on each processor. And so actually what we want to do is that at every stage we have the same amount of elements that are active. So here in this case, this is an ideal case. We have 3 red elements, 3 green, and 2 blue. And so then we should have nothing to wait unless we have to wait due to communication. But the communication will be very high, not only because you cut 4 elements interfaces, but also because they have a high weight, because you have two neighbor elements that have a multirate load 8, and so they will have to communicate a lot more than the 2 elements that have a multirate load 2. So in practice, what we do is we use the METIS multi-constraint graph partitioner, and we assign vectors of constraints that correspond to the amount of different multirate loads that we have, and we give only, we say, will an element be active at one moment of the algorithm, and then we put 1 or 0 if he is active or not at one moment of the algorithm. And so METIS is able to tries to find, it's a heuristic, it tries to find the best partitioning that respects these constraints. And we also assign these number of communication loads about the number of communications that will be performed between 2 elements, so that the objective is to to have the mean weighted edge cut, mean multirate weighted edge cut. So the parallel multirate algorithm, this is a bit long, but I just try to explain you a bit in detail how this works. So again, for example, here you have the ghost elements and the other elements with the multirate tags. So in the table up, you have the multirate tags in horizontal and the number of stages in vertical. And I differentiate the volume terms, the intra-processor interface terms, and the inter-processor interface terms. So this is to allow the difference between all these terms is because we want to do non-blocking operations and do as much as computation possible when we communicate. So first we compute the current input on every node of the mesh. We don't scatter anything at that point. We send the information to the other partition while we compute the volume terms of each element and the intra-processor terms. After that, we receive all the current inputs on the nodes, and we are able to compute the inter-processor interfaces. This is after I represented for each stage, but after that, you will have only the tag 0 and 2 that will be active, but you need the current input of the neighboring group number 3. So you compute the input, you compute the volume and inter-processor interfaces for K2, and after that, also you receive the information, you compute the inter-processor interface residuals, and after that, here you can compute your next step solution for the smallest multirate group, and so on. Here, the multirate group, he will have 4 stages, so here I have a 3, and I still need the next neighboring elements, and I compute again like this. After that 4th stage, I have 3 groups that are at level UN plus 1/2, so I computed the next step solution at 1/2, and so on. And finally, every element is at time step UN plus 1. So practical applications, results about this parallel multirate algorithm. Here is an academic test case, the Stommelgear test cases, about 650,000 triangles. We use P1 DG spatial discretization, and we just use an arbitrary linear refinement from one corner to the other. So here you see clearly all the Bell groups that are separated at each time by all these buffer elements in black that are here of size 2. We choose the classical no optimization for the speedup alpha equals 1. And so on the left you see all the subdivisions of all the number of elements that belong to each group and the time step associated with the multirate exponent and the multirate load. So here we have a ratio about 180 between them, between the smallest and the largest time step, and the speedup that the theoretical speedup that we would achieve is 6.85, and 9.37% of the buffer elements cover the entire mesh. So about the quality of the mesh partitioning, the 2 first graphs represent on the left, on the top left, actually the total communication volume that we will have to perform during a certain amount of time. And we see actually that, here we compare the three partitioning strategies. And we see that, as expected, the highest number of communication is performed by the multi-constraint MP, multi-constraint partitioning. Also, for the estimated computation to communication ratio, communication to computation ratio, it's increasing very fast for the multi-constraint partitioning, because also we have a lot more of computation, smaller computation to do up to higher number of processors, but also a high number of communication. Here we plotted on the on the left. We plotted the global load imbalance that we will have. But there, the multi-constraint partitioning strategy is very good. We imposed a load imbalance of 1.03 to meters for these constraints, and we see that the multi-constraint partitioning is almost perfect, stays under this critical value. And that, as expected, the classical partitioning strategy, we have rapidly something that is really bad, an imbalance of almost 7, and the single constraint partitioning is better, but not as good, certainly not as good as the multi-constraint partitioning. Here we represented the effective computed imbalance. So we computed actually the scaling, the wall clock time, and we compared it on multiple processor compared to on only one processor. And as we can see, the solid lines are a bit as expected for the green and the red ones, so for the multi-constraint and classical partitioning, but not for the single constraint partitioning. And actually, this is because the workload is well balanced, and for a high number of processors, some computation will be performed more rapidly and won't have to wait really to synchronize because of these non-blocking communications. They still can continue and compute some things, especially when you have a high number of processors and small number of elements per processor. But what I wanted to show with the dashed lines is that if you put a barrier that you force your algorithm to stop and wait all the processors at every synchronization time step, you will obtain these dashed lines, and you see that it's much more like what we expect from our theoretical point of view of partitioning. So here are illustrations of the partitioning for the classical partitioning for 8 partitions. So we see that here we had a bad imbalance for the multirate setup. The single constraint, so all these partitions are contiguous, but for the multi-constraint partitioning, sure, we can find something with all the partitions that are really contiguous. But we have a very good load imbalance about computation. We have a high number of communication, but we see that even if we have different methods find a good mesh partitioning, they are not contiguous, but they are still in contiguous patches everywhere. And we see that all the colors, we need to use big elements and subdivide it there and have different patches. So these are results for the strong scaling results with respect to the wall clock time on one single processor for this case, for the 3 partitioning strategies. So you see that the multi-constraint partitioning is the most efficient. Actually, here on your left, this is pure speed up compared to the multirate, the actual multirate time taken on one single processor. On the graph on your right, what we computed here is we do the strong scaling, but compared to the time taken on one processor, but for single rate. And so we can see that originally the speed up was something like 6.8, and that for 128 processor in total, we even benefit from the fact that the actual speed up even on a single processor is a bit higher than the theoretical one that we expect. And so we have a very good scaling for the multi-constraint partitioning strategy and we are at a total speed up compared to the time for one processor single rate up to 750, something like that. Here we do more comparison about the effect of using a different number of temporal refinements. So what I show in the table is that for if you choose different number of temporal refinements, you will have different speedups. So for for the single rate, the case where Z star is 0, you have 1, and after that your speedup increases. But at one stage, it becomes you add a multirate group, but there are not as many elements as in the other groups, and the multirate speedup will be quite the same, just a few % difference due to add a temporal refinement. So we can imagine that taking less multirate groups will imply that we will have less constraints for our multirate strategy, and so maybe find better partitionings and find a better solution with a less weighted edge cut. So again, we compared here the total communication, the communication to computation ratio. So we see that the highest is for the highest number of temporal refinements, and that it is less for the case with single rate. But for the total communication volume, we can clearly see that actually the worst one is the single rate one. Why? Because sure, you reduce the computation, the total computation, but if you think about only communication, for the same amount, for the same global time step, the period time period that you want to achieve, you will have to perform less communication than in the single rate case. Here under you have an illustration of the global load imbalance. So you see that there everything remains under the tolerance imposed to Métis, that is 1.03, but the way the load imbalance behave is not really clear. We see it's a heuristic, so it tries to find the best partitioning, but it's not. We can't see really imagine that something is. But we see that the highest the multirate exponents, that's the number of temporal refinement, the highest. It seems to have a tendency to be higher for the multi-constraint partitioning with high number of temporal refinements. So here again, the strong scalings for all the multirate exponents on the left compared to the actual multirate time taken on one processor, there compared to the single rate time taken on one single processor. So you see that actually taking a higher number of temporal refinements still gives you in total, even if on the left side you see that the total speedup, the intrinsic scaling decreases, but in total, since you have a good speedup, theoretical speedup, you still achieve better results by using a high number of temporal refinements. Here's the most practical application I presented before, the Japan tsunami application. We use P2DG spatial discretization. We achieve a speedup, a theoretical speedup of 9.32. Here we choose to take a smaller number of temporal refinements because in total normally it's something like 12, because you see that the ratio is very high, but the number of big elements is so small that you have only like 0.01% difference in the theoretical speedup, and so we kept the number of temporal refinements to something acceptable and don't have to perform so much time step to compute it, and you will have more solutions. So again, here the multirate groups and a zoom again for the two-stage method. Here are partitions for the multi-constraint partition for 16 partitions on the zoom and on the world mesh. Again, the total communication volume, the computation to communication ratio, we see that it's compared single rate and only multi-rate. So you see that clearly, again, the total communication volume is a lot lower for multi-rate, but that the communication to communication ratio goes very higher for the multi-rate case than for the single rate case, because this ratio is, even if the communication is lower, the ratio is very high. But still, here again we compare, it's on another machine up to 256 processors. We compare the single rate and multi-rate case, and we see that still here we achieve a very acceptable speed up. 256 processor in total. We are more than we are 2,500 times faster than the single rate method on one processor. Here are just illustrations to show you the results of the tsunami simulation to show that apparently we have quite the same result with single rate and multi-rate. This was performed on 64 processors. Last, we wanted to treat a 3D case, the acoustic propagation in turbofan engine intake. So this is not really a marine modeling, but in our model we are not really able for the moment to do 3D real 3D test cases for shallow waters for ocean modeling, and still we have to explore how multi-rate could be adapted to the 3D time stepping issues. So this is just a CFD case. So we have almost 50,000 tetrahedral elements. We use P3 discretization. We use the maximum number of temporal refinements. You can see that even here we have only 286 elements in the smallest multi-rate load group, and the speedup is 10.911, and you see here in white this time the buffer elements that separates each time all the bulk groups from the buffer group. Finally, again, the communication volume, the communication to computation ratio, and we see also that even for the small number of elements, but with a higher order of discretization, we still achieve some really acceptable speedup, and it's still very efficient to use multi-rate in parallel up to a high number of processors compared to single rate. Here are some solutions of the pressure fields after a certain time in the turbofan. Finally, ongoing work. Just to say that multi-rate can easily be adapted to wetting and drying methods. We try to work on it a little bit just to show that that it works, but we still have some stability issues with the method. It was a method implemented, proposed by Tuomas Kärnä from our group. But there are still stability issues there, and the parameters that we have to choose, that were chosen for the original method, should be different, I think, in the multi-rate context. We could also use dynamic multi-rate and to solve this, because maybe some things changes too fast. We also want to think about the tracers. We haven't think yet about the tracers. How could we couple this, the tracer advection equation with this? So conclusion and perspectives. I think we showed that multi-rate methods are well suited for DG on unstructured meshes. We observed considerable speedups for realistic test cases for marine flows. Many features, especially as the simplicity of the implementation of classical single-rate explicit Runge-Kutta methods, are preserved. By using an appropriate partitioning strategy and adapting the global multi-rate algorithm, we show that the parallel performance is still good with multi-rate setups. And we showed before that the global accuracy is comparable to single-rate for low spatial discretization orders. For the future, we think about working on dynamic multi-rate. So here it was only static, so maybe we have to decide if it's worth to change the multi-rate groups when the physics changes, if you use different meshes, moving meshes, or whatever. When is it worth to change the multi-rate groups, and when is it worth also to repartitioning the mesh? So this is more adaptivity in a multi-rate context. We should think about that. Is it worth to do that all the time? Because it's also costly to compute these groups and the partitionings. I think we can still do some efforts on improving the scalability, parallel scalability. Could maybe think more about memory access and storage. Maybe think about how you distribute the partitions on the different nodes of your cluster. So try maybe to put different, to try to improve the contiguity, the intra-node contiguity of the repartition of the mesh partition. So that are ideas. So I think I'm done. Thank you very much. If you have any questions, I'm open to answer.
That's really, that's a lot to take in. Any questions?
Yeah, so you probably already showed a slide on this, but you had a lot of slides, so.
Yeah.
So maybe it's just a matter of going back to one of the slides. But there's two reasons for doing multi-rate. One is the obvious advantages in that you can take smaller time steps only in the areas where you need a smaller time step. But the other advantage is that you're not losing accuracy in the coarse regions. Ideally you want to take, if on the coarse region you had to take a really tiny time step, that would presumably affect your accuracy. Do you show slides? Did you show anything that suggested that in fact the accuracy is improved by, or to what extent is the accuracy improved by
actually
sort of allowing a larger time step on the coarse grid?
No, not really. I just
That would normally be
I just showed the it was the part of the slides. So this was the convergence, but in terms of CPU time, it's clear that we have the best the best, even for accuracy, that we have in globally the best ratio, the best results. But it's sure that for temporal error, as I said, as you use as in the single rate case, even if you have coarse elements, you will use a small time step. The pure temporal error will be effectively very small compared to the multirate, because there the biggest elements, you will have a larger error, and this will propagate due to the communication, to the interface fluxes. It will arrive to all the elements and it will propagate. And actually, if you analyze this graph a little more, you see that the first points of the same single rate and multi-rate methods. And since for this example we have 5 temporal refinements, actually we'll see that the difference in temporal error is exactly the same ratio 2 exponent 4 of 5 between. So you have a difference that you can remark that the difference is exactly the same, so that effectively the error propagates from the largest time step to all the elements. And so that purely temporal, you can see this ratio between single rate and multi-rate that is respected, actually. So I don't know if it answers your...
I'm not sure either, but I can ask you about it later.
Well, but at a fixed spatial resolution, the accuracy is controlled by the coarsest time step, which is the exact same thing we showed in the shallow water test cases, but flipped. For a fixed time step, the accuracy was controlled by the coarsest grid spacing. It's the hyperbolic nature of the problem.
But you see, it depends also on problems that you're solving, like in this say tsunami wave propagation, right, where it passes to the coarse part after the event, right? So you don't care that much, and what you care is fine resolution parts where error is small. Right? So it really
You still need to resolve the
you still
coarse.
need to resolve that everything say goes away, right? That there is no reflections. That's why you need to resolve it. You don't care about this coarse part. So it's not necessarily that error is that globally propagated, like you see, like in the ocean case. If you're doing say Arctic Ocean finally resolved, the coarse ocean is say influencing, but on very large time scale, the errors that you are getting locally.
Yeah, but it's a separate problem, because there is one question, which is that the spatial error propagates from the big element to the small element, and this is independent of the temporal discretization. And then there is the temporal error discretization that actually is bigger with multi-rate, but we don't really care, because for explicit temporal discretization, the constraint of the time step for stability reason, is so strong that the temporal error is always much smaller than the spatial discretization error. So we don't really care about the temporal error introduced by the multirate.
Perhaps a clarification. When you partition the domain, is your primary criterion the spacing between the points or CFL? So you are trying to have similar CFL in one of the subdomains?
You mean the partitions for parallel or the partitions,
Well,
the groups, the multi-array groups?
Even for the time stepping, yes? So
Yeah.
you are trying to match the similar CFL in the subdomain?
Yeah, we compute the actual CFL of each element locally, and after that we determine the range of multiples of the time step that you use, and after that but this is the construction. So first you attribute an actual range of time steps to which an element will belong, just by putting him in this group, and after that you construct effectively the multirate setup with the buffer elements and smooth thing to have. So it's sure that you lose something compared to.
Okay, that's what I thought. Does it mean that if you have a mesh and you partitioned it, for one example, if you change flow conditions, you need to repartition it again?
Yeah.
So what is
Yeah,
the
it depends on-
overhead? Yes. So what is the overhead? What is the cost of partitioning?
I should maybe show something, but I don't have it here. But
Okay.
in general, it really depends on it's completely dependent on the problem size.
It's much smaller than the.
Yeah. It's maybe it's maybe one or two iterations in practice or something like that. So what you gain. But if you have to add the partitioning on multiple processor, you also have to add something. But in general, it's really fast. It's really not that slow. You just have to go on all the elements and do this smoothing and allocation process, and it's not. So that's what I say about future work. Is think about this. We had two master students that tried to a little bit explore this path to say, even in the sequential case, just to say, if we have physics that changes, we recompute, we do an estimation, we try to find an estimator of, will it change a lot? Will we just reduce the global time step of all the elements and just keep the same groups, but reducing the time step of increasing it, depending on the physics? Or do we need to recompute the groups to say, no, there we're losing too much efficiency, it's worse to recompute all the groups? Because you could just keep the same groups, especially if you have the same grid size, you keep the same elements, but the physics changes, so you say, okay, no, I will be unstable, so I decrease the time step for all the groups. But you keep the same ratios of and so then it's just thinking about, will it be worth or not to recompute these groups at one moment, because the speed up will change so much. You will have, maybe you will decrease, you will be back to single rate, and you could do something else and have again a good speed up. So this is, we think about it, but for the moment we did it only for static problems where we just compute static CFLs.
Was the searching algorithm for, what was the partitioning algorithm for 3D in your intake? You had relatively little elements, tetrahedral elements, I think it was less than 500,000 or something?
For the 3D test case, 50,000.
15,000.
50.
50,
Yeah.
It's still kind of moderate with what we may anticipate later on. Was the increase in the cost of pre-processing for partitioning dramatically increased by comparison with your 2D effort?
No, not much. But the 3D test case, I just finished it this week, so I haven't made much analysis, but I haven't done this to compare effectively the partitioning depending on the.
Okay. Well, thanks again, Bruno.
Thank you.